Lesson: Overfitting and Underfitting, Strategies for Model Optimization. Overfitting and underfitting are critical concepts in machine learning, influencing the effectiveness and generalizability of models. These phenomena occur when a model learns either too much or too little from the training data, respectively. Understanding and addressing these issues is crucial for optimizing machine learning models, ensuring they perform well on unseen data. This lesson focuses on actionable strategies, practical tools, and frameworks to mitigate overfitting and underfitting, enhancing proficiency in model optimization. Overfitting occurs when a model captures noise in the training data, resulting in excellent performance on the training set but poor generalization to new data. This is akin to memorizing answers for an exam rather than understanding the material. Overfitting is particularly prevalent in complex models with a high number of parameters, such as deep neural networks. For instance, a study by Goodfellow, Bengio, and Courville highlights how overparameterized models can fit random labels, demonstrating the model's capacity to memorize data rather than learning meaningful patterns. Conversely, underfitting happens when a model is too simple to capture the underlying trends in the data, leading to poor performance on both training and test sets. This often occurs when the model is not complex enough or when insufficient training time is allocated. An example can be seen in linear regression applied to nonlinear data, where the model fails to capture the complexity of the data relationships. To combat these issues, several strategies can be employed. One fundamental approach is the use of more data, which can help models generalize better by providing a more comprehensive view of the underlying distribution. However, acquiring additional data is not always feasible, prompting the need for alternative solutions. Regularization techniques are powerful tools for addressing overfitting. These methods add a penalty to the loss function to discourage complex models. L1 and L2 regularization are common techniques that add a penalty proportional to the absolute sum of coefficients or the square of the coefficients, respectively. By doing so, they effectively constrain the model, reducing the risk of overfitting. Dropout is another regularization technique specifically designed for neural networks. It involves randomly dropping units during training, which prevents the network from becoming overly reliant on any single feature. This method has proven effective in reducing overfitting in deep learning models, as evidenced by its widespread use in practice. Cross-validation is a robust technique to evaluate model performance and prevent overfitting. By partitioning the data into training and test sets multiple times, cross-validation ensures that the model's performance is consistent across different subsets of data. K-fold cross-validation, where the data is divided into K subsets and the model is trained and evaluated K times, is a popular choice that provides a reliable estimate of model performance. Hyperparameter tuning is another critical aspect of model optimization. Grid search and random search are traditional approaches, but more sophisticated methods like Bayesian optimization and genetic algorithms offer greater efficiency and effectiveness. These techniques systematically search for the optimal hyperparameters, improving model performance and mitigating overfitting. Ensemble methods, such as bagging and boosting, are powerful strategies to enhance model robustness. Bagging, exemplified by random forests, involves training multiple models on different subsets of the data and averaging their predictions. This reduces variance and helps prevent overfitting. Boosting, as seen in models like XGBoost, sequentially trains models, each correcting the errors of the previous ones, leading to strong performance even on complex datasets. In contrast, addressing underfitting often involves increasing model complexity. This can be achieved by adding more features, increasing the number of parameters, or using more sophisticated algorithms. For instance, transforming a linear model into a polynomial one can capture nonlinear relationships in the data, reducing underfitting. Feature engineering plays a crucial role in combating both overfitting and underfitting. By carefully selecting and transforming features, practitioners can provide models with the most relevant information. Techniques like principal component analysis and T-distributed stochastic neighbor embedding can help reduce dimensionality and highlight important patterns in the data. Data augmentation, particularly in fields like image processing, can effectively increase the diversity of the training data without the need for additional data collection. Techniques such as rotation, scaling, and flipping images have been shown to improve model robustness, reducing both overfitting and underfitting. Frameworks like TensorFlow and PyTorch provide built-in functionalities for many of these strategies, making implementation straightforward. TensorFlow's Keras API, for instance, allows easy integration of dropout layers, batch normalization, and other regularization techniques. PyTorch offers similar capabilities, with its flexible design facilitating the customization of models and training procedures. Case studies highlight the real-world application of these strategies. For example, the ImageNet Large-Scale Visual Recognition Challenge has seen significant improvements in model performance due to the adoption of techniques like dropout, data augmentation, and ensemble methods. These strategies have enabled models to achieve state-of-the-art accuracy, demonstrating their effectiveness in practice. Statistics further support the importance of addressing overfitting and underfitting. A study by Caruana et al. Found that models employing ensemble methods achieved a 10% improvement in classification accuracy compared to single models. This underscores the potential of combining multiple strategies to optimize model performance. In conclusion, addressing overfitting and underfitting requires a multifaceted approach, leveraging a combination of data-centric and model-centric strategies. By employing techniques such as regularization, cross-validation, hyperparameter tuning, and ensemble methods, practitioners can enhance model generalization and robustness. Practical tools and frameworks like TensorFlow and PyTorch facilitate the implementation of these strategies, making them accessible to professionals seeking to optimize their models. Through continuous learning and adaptation of these techniques, machine learning professionals can successfully navigate the challenges of overfitting and underfitting, ensuring their models perform effectively in real-world applications.